Alright, this is week 22 of AP Physics, and in this lesson we'll go over the following. We're going to talk about some problems involving momentum and impulse, and we're also going to go ahead and talk about conservation of momentum. For our lesson objective, we'll be looking at how you students can solve for the law of conservation of momentum problems. So let's go ahead and get started with an example. In example 2, they ask you this the following. In a crash test, a car with a mass 1.5 times 10 to 3 kilograms collides with a wall and rebounds. The initial and final velocities of the car are -15 because it's traveling to the left, and then after it rebounds away from the wall, it's positive 2.6 meters per second respectively. If the collision lasts a total of 0.15 seconds, then A, find the impulse delivered to the car due to the collision. Alright, let's start with part A, then we'll move on to part B after that. Alright, so we're looking for impulse, and the formula for impulse, I for impulse, is force multiplied times time. Now force times time, we know that that's also equal to the change in momentum. So the change in momentum, which is momentum final minus momentum initial, which is mass times velocity final minus mass times velocity initial. Now this formula we can go ahead and simplify a little bit and factor out the m. We'll probably end up doing that for solving for part A, find the impulse. And for this problem, let's go ahead and go back and get all the information that we had in the previous slide. So we know the mass of the vehicle, it is 1.5 times 10 to 3 kilograms, that is 1,500 kilograms. We also know that the velocity initial, it's equal to -15 meters per second. Velocity final after rebound was 2.6 meters per second. And again, the time for the collision is a grand total of 0.15 seconds. Alright, so that's all the information that's given to us. And again, part A, find the impulse. So for impulse, alright, what we can do is we have the mass of the vehicle and we have the initial and final velocities of the vehicle. So we're going to go ahead and use those to go ahead and figure that out. So impulse is equal to mass. I'm going to factor out the mass. It's going to be velocity final minus velocity initial. And that's going to go ahead and give us a formula for impulse in part A. So now we plug in the mass, which is 1,500 kilograms for the vehicle. Velocity final, which is 2.6 meters per second, minus, the formula's got a negative there, -15 meters per second. Alright, and once you solve for this, we'll have our answer for initial. I do want to point out that here we have a negative from the formula and a negative because of the direction of the initial velocity of the vehicle is towards the left, which is negative in this problem. So a negative times a negative will give me a positive, so it's going to be really 2.6 plus 15, so it gives us 17.6, and then we multiply that times the 1,500, the mass of the vehicle, and we end up with our answer for the impulse is 26,400 kilograms times meter per second. So that is part A of this problem, find the impulse. In part B, they asked us for the magnitude and direction of the average force exerted on the car. So now we're looking for the force. Alright, so if you look at this formula, force is equal to impulse over time. Okay, so we're going to go ahead and use the impulse which we just solved for and use this formula right here to go ahead and solve for the force. Okay, so impulse is equal to force times time, and now we're looking for the force. So I'm going to go ahead and divide by time on both sides, and that's going to give me force is equal to impulse over time. So that's how I'm going to go ahead and solve for the force in part B. So force is equal to impulse over time, and the impulse was 26,400 kilograms times meters per second, divided by the time of the collision, which is 0.15, that was given to us. And we go ahead and divide both of those numbers, and we end up with the force, which is 176,000 newtons. And that takes care of example number 2. Alright, let's go ahead and move along to our next problem. Problem number 3, we're asked the following question. When a person is involved in a car accident, why is the likelihood of injury greater in a head-on collision as opposed to being hit from behind? Answer using the concepts of relative velocity, momentum, and average force. Alright, so let's go ahead and do that. All right, so let's go ahead and figure out a problem. Let's say that you have a truck traveling, and it's traveling towards the right at 15 meters per second. I'm going to put positive because it's going to the right. And then you have another car that is traveling at 5 meters per second. So I'm going to put negative 5 meters per second because it's traveling to the left. Alright, so what is the change in velocity here? The change in velocity for both of these would be a grand total of 20 meters per second. 15 and 5, that would be the change in velocity. Velocity of car, let's call this guy A, minus velocity car B. So it's going to be 15 minus negative 5. That's going to give us 20 meters per second. That'll be the change in velocity. So it's a quite large change in velocity, which means that you're going to have a lot of force in this collision. On the other hand, what if the car was heading the other direction? So we're going to put the truck going the same direction, positive direction. Still same velocity, 15 meters per second. But it's going to be not a head-on crash, but instead rear end. So the car's going away from the truck. So now I'm going to put a plus 5 meters per second. So the truck's going to rear end the car. What is our change in velocity now? The change in velocity, velocity A, which is our truck, minus velocity B, is going to be 15 minus 5. So that's going to go ahead and give us a change in velocity of 10 meters per second. So in the head-on collision, the change in velocity is much greater than a rear-end collision. So therefore, the head-on collision will also give you a larger change in momentum, and a change in momentum will also give you a larger force, assuming that the time for the head-on collision and rear-end collision is the same amount of time. That's going to give you a lot more force. All right, so that takes care of example 3. In example 4, they ask you guys, suppose the car doesn't rebound off the wall, but the time interval of the collision remains the same at 0.15. In this case, the final velocity of the car is 0. Find the average force exerted on the car. Alright, so let's go ahead and solve that problem. So it piggybacks on the first example that we did. And in that problem, they gave us some information such as the mass of the car. So I'm going to go ahead and rewrite it, 1,500 kilograms. They also gave us the initial velocity of the car, which was negative 15 meters per second, because it was traveling towards the left. And this time though, they're saying no, the final velocity, there's no rebound, so the car comes to rest. So it's got no velocity, 0 meters per second, but the collision still takes the same amount of time at 0.15 seconds. Alright, so what is the average force for this vehicle? Alright, so here's going to be our formula. We know that force times time is equal to change in momentum. Right? So I want to go ahead and what is change in momentum? Well, change in momentum is mass times velocity final minus velocity initial. We're going to go ahead and divide by t on both sides, so we're going to isolate the f, and that's our force. So that's going to be our formula right there. So force equals the mass, which is 1,500 kilograms, multiplied times the change in velocity, 0 minus negative 15, over the time 0.15 seconds. Alright, so that is our formula. We're going to go ahead and plug all of these values into the calculator and come up with the answer. So it's going to be 15 times 1,500 divided by 0.15, a grand total of 150,000 newtons of force when the car comes to rest after the collision against the wall. Alright, that's problem number 4. Let's go ahead and move along to our next problem. For this one, in problem number 5, they ask you, a person applies an impulse of 5 kilograms times meter per second to a box in order to set it in motion. If the person is in contact with the box for 0.25 seconds, what is the average force exerted by the person on the box? Alright, so for this problem, we're going to assume that the box was at rest at the very beginning. Alright, now the person is in contact for 0.25 seconds, so they go ahead and they give us the impulse that the person gave us, 5 kilograms times meters per second, and they also give us the time. They're only in contact for a quarter of a second. Alright, and the question is, what is the average force? Question mark there. Alright, so we're going to go ahead and use this formula right here. Impulse equals force times time, because we're solving for the force. So if impulse equals force times time, we want to isolate the force. We're going to divide both sides by time. And there we have it. It's going to be impulse over time to give us the answer for this problem. So force is equal to impulse, which is given to us at 5 kilograms times meter per second, over the time, which is just a quarter. Alright, and our answer comes out to be 5 divided by 0.25. That is 20 newtons. So for this problem, it will be letter D is our answer. Let's go ahead and move along to problem number 6. Problem number 6 says a student dropped an object from rest above a force plate that records information about the force exerted on the object as a function of time during the time interval in which an object is in contact with the force plate. Which of the following measurements should the student take in addition to the measurements from the force plate to determine the change in momentum of the object from immediately before the collision to immediately after the collision? Alright, so quick reminder, what did the force plate tell us? Okay, it told us the force, it records a force as a function of time. So it both tells us the force that was applied plus the amount of time that force was applied. So it tells us those two things, force and time. Alright, and what are we trying to determine? The change in momentum. Now we know that force and time equals change in momentum. Alright, so according to our formula, let me erase the rest of this. Force multiplied times time, that equals change in momentum. So they're saying, what else do we need aside from force and time to figure out the change in momentum? The answer is, that's all we need. So for all of these, the answer will be letter D. The student has enough information to make the determination. So that's the answer for problem number 6. And problem number 7 says the student obtains data on the magnitude of force applied to an object as a function of time and displays the data on the graph above. That's on the next slide. Answer the following questions for the information and diagram. So it says the increase in momentum of the object from T0 to T4 is most nearly, so we're looking for what is the increase in momentum, or another way of saying it would be, we're looking for what is the change in momentum. Alright, so that's what we're looking for. Alright, and they give us this graph to figure it out. So we want to know what is the change in momentum. So I'm going to go ahead and take a moment to write down the formula. We know that force multiplied times time is equal to the change in momentum, and that's what we're looking for. And the graph here is, on the y-axis is force, and that's as a function of time on the x-axis. Alright, so we have force and time for this graph. So what do we have to do to figure out the change in momentum from this graph? The answer is, notice how we are multiplying them together. When you multiply them together, that means you find the area under the line. So you would draw a best fit line under here and go ahead and find the area under the line, and that's going to go ahead and give us the answer. So let's go ahead and do that very quickly. So we're at 5 and it goes to 25, and that takes here from 0 to 4 seconds. So we're going to go ahead and find the area. I'm going to break it down into 2 parts. Alright, and I'm going to find the area of this triangle right here. So I'm going to go ahead and change colors to red for the triangle part. Alright, so what is the height from here to there? That's 5, that's 25, so therefore the height is 20. And from here to there is from 0 to 4, so that is 4. So therefore, how do you find the area of a triangle? It's 1/2 base times height. So it will be 1/2 the base, which is 4, times the height, which is 20. So that's going to go ahead and give us a total of 40. Alright, next, let's find the area of the rectangle, which is down here. Alright, the height is from 0 to 5, so it's 5 height, 5 times 4. So area of a rectangle is just base times height. So it's going to be 5 times 4. That gives us 20. Alright, so what's the total area then? 20 plus 40, that'll give us 60. So the answer for this problem is 60. Letter C. Another way you can approach this problem is, rather than separating into a triangle and a rectangle to figure out the formula, or the area under the line, you could have said also, well, what's the average force? So for example, that's a 5, that's a 25, add them together, that's a 30. So what's the average? That would be a 15, right? Because 15 is half of 25 plus 5 divided by 2. All right, so the average force was 15. So 15 times 4, 60. That would have been another way of solving this problem. All right, let's go ahead and move forward then to our next problem. In this problem, it says a ball with a mass of 1 kilogram is released from rest above a horizontal surface. The ball falls downwards and collides with the surface with a speed of 2 meters per second. The average force exerted during the collision is 20 newtons over a time interval of 0.1 seconds. Which of the following best predicts what will happen to the ball immediately after the collision? All right, and we got our 4 predictions right here. It says the ball will come to rest on the surface. The ball will bounce up from the surface with a speed lower than what it had before the collision. The ball will bounce up from the surface with the same speed as it had before the collision, and the ball will bounce up from the surface with a speed greater than that it had before the collision. So those are our 4 options. So let's go ahead and figure out what will be the final velocity after the collision. So what we're going to go ahead and use is force is equal to the change in momentum. So force times time is equal to change in momentum, which is force times time is equal to mass times velocity final minus velocity initial. All right, so what we're going to do now is isolate the velocity final. That's what we're trying to solve for. So we're going to move the m over to the left side of the formula so we can go ahead and begin to isolate the f, the velocity final. So that gives us the following. And now we're going to go ahead and get rid of the VI by moving over to the left side. So that's a negative, so I'm going to go ahead and add VI to both sides. So here's our formula. Force times time over mass plus velocity initial is equal to velocity final. All right, so let's go ahead and plug in the values for this and come up with the answer. All right, so now velocity final, it's equal to force. The force was 20 newtons. The the time was 0.1 second. The mass is 1 kilogram plus the velocity initial. Now velocity initial, they told us, and let me switch to the slide, it was 2 meters per second, but it is going in the downward direction. So I'm going to go ahead and, rather than put just 2, it should actually be negative 2. So plus negative 2 meters per second, all right, because it is going in the downward direction. Now let's go ahead and plug it into the formula. So it is 20 times 0.1 divided by 1 minus 2 gives us a final velocity of 0 meters per second, meaning that at the end, this ball has no velocity. So the answer is A, the ball comes to rest on the surface. All right, that takes care of problem number 8. Next, we're going to go ahead and talk about conservational momentum. So it states up there, the law of conservational momentum tells us that the total momentum of a system is conserved when a collision occurs in a closed, isolated system. So momentum is conserved. So that leads us to this formula where the momentum for object 1 plus momentum of number 2 initial is equal to momentum of object number 1 plus object number 2 final. They equal to each other because in a closed, isolated system, momentum is conserved. Now, I also want to go ahead and show you a couple more formulas where, well, the first formula is if two objects are separate, they come together and then they bounce off of each other and stay separate. But what happens if they start together and then they separate? So for example, in this one, notice that the two masses are combined. What happens if you have a person holding a football and they throw it? So they began together, he was holding it, and then they threw it. Now they're separate. That will be what the formula is. Notice that the masses are in parentheses added together. All right, on the other hand, what if you have a person catching that football? All right, what would the formula look like? Initially, they were separate. The football's in the air and the person's waiting for it. So it's two separate objects, and at the end, now he catches it, they are together. All right, so that's why you see both masses together in the parentheses. So it's a modification of our initial formula, this one. For, again, this one, if two objects are separate, they collide, and now they separate again, you use this one. If they start together and separate, you would use this formula. And if they start separate and come together, you would use this formula as well. Alright, so those are the variations of the conservation of momentum formula. Let's go ahead and do some problems. Example 3. You have an archer. An archer stands at rest on a frictionless ice. His total mass, including his bow and quiver of arrows, is 60 kilograms. For part A, it says if the archer fires a 0.03 kilogram arrow horizontally at 50 meters per second in the positive x direction, what is the subsequent velocity across the ice? Once he launches it, the arrow is going to go in one direction, but the archer is going to go in the opposite direction. So we want to know what is his velocity as he slides across the ice. The reason why they're solving this problem while he's standing on ice is because they want you to ignore friction. So if he was just standing on regular ground, there's not enough force to really get him moving. So that's why they said, let's do ice, so that way you can go ahead and ignore friction. So we're going to go ahead and do that as well. So let's go ahead and write down all the information that's given to us. Both of them together is 60 kilograms. That is the archer and the arrow all together. Mass of the arrow, it's going to go ahead and be very small at 0.03 kilograms. So therefore the mass of our archer, it's going to be the total minus the mass of the arrow. So it's going to be 60 minus 0.03. So it's going to give us 59.97 kilograms. That's the mass of the archer. Alright, now the velocity of the arrow he fires at, velocity final of the arrow, is going to go ahead and be 50 meters per second. That is for our arrow. And now the velocity for the person is what you're looking for. Velocity final of our archer is still an A. We're going to label our archer letter B and letter A for the arrow, so we can keep them straight. So that's what we're solving for. By the way, initial velocity for both was 0 meters per second. As the archer was there stretching as his bow, he was not moving. Alright, so let's go ahead and figure out, so for the velocity of the archer after the arrow has been fired, how far is, or how quickly is he moving backwards? Alright, so which formula should we use? Well, let's go ahead and take a look at our formulas. And this one will be it. Why? Because they started together and now they're going to go ahead and separate. Alright, so that's the formula I'm going to go ahead and use. I'll write it up here. M1 plus M2, velocity initial, it's equal to M1 V1 final plus M2 V2 final. Alright, so that's what we got here. Now, M1 plus M2, that is the total mass, right? Is 60 was the archer plus the arrow. Initial velocity, the archer was stationary, so it's 0. So really this whole left side is going to be a 0 equals mass times velocity initial of object 1. I'm going to change these guys to object 1. Who? The arrow is object 1, the archer is going to be object 2. And M1, M2 times V2 times final. Alright, so what are we looking for? We're really looking for the velocity final of our archer. So that's what we're solving for. Alright, so I'm going to begin by moving over the mass times velocity initial. Alright, so mass times velocity of object 1 final, pardon me, negative. Alright, and now I'm going to go ahead and divide both by mass of object number 2 to isolate velocity final of object number 2. So this will be our formula, M1 V1 final over M2 equals velocity of object 2 final. Alright, so that is our formula. Let's go ahead and plug in the values to go ahead and solve for that. So V2 final, it's equal to mass. The mass of the arrow was 0.030 kilograms. Velocity final of the arrow was 50 meters per second over the mass of our archer, which was 59.97 kilograms. Alright, that is our answer, velocity 2 final. notice it will be negative, and that's fine because the arrow is positive and the arrow is going in one direction. The archer is going to go in the opposite direction, so that's why it's going to be a negative answer. So 0.03 times 50 divided by 59.97 is going to go ahead and give us a velocity of 0.025 meters per second, negative. Very slowly he'll slide across the ice because, well, the mass of the arrow is very small. Alright, so that takes care of part A of this example. Let's go ahead and look at part B. Alright, in part B we're asked, he then fires a second identical arrow at the same speed relative to the ground, but at an angle of 30 degrees above the horizontal. Find his new speed. Alright, so we have a second identical arrow that he's firing. Alright, so the mass of the arrow stays the same. We're going to assume that the velocity of the arrow remains the same, but this time it's at an angle of 30 degrees. Alright, now should we change the mass again? Yeah, let's go ahead and do that because he's getting a second arrow. It's identical, so therefore when he launches it, his mass, well, that's the mass of the archer. That's going to archer plus whatever other arrow he has. Let's just keep it at 59.97. Alright, so this new arrow is going at an angle of 30 degrees. Now what we want to do is figure out what is the velocity of this arrow on the x-axis. We don't care about the velocity of the arrow on the y-axis, and the reason why is because that is not going to affect how much he slides backwards on the x-axis. Alright, so we only care about what is the velocity now on the x-axis, so let's go ahead and get that. So the velocity of the arrow is at 50 meters per second, but now it's at 30 degrees. But I want the velocity final of the arrow on the x-axis. Alright, so this component of our vector, that's what I'm looking for. So notice how it is adjacent to the angle, and we have the hypotenuse, so it's going to be cosine of theta. It's equal to velocity final of object 1 on the x-axis over the hypotenuse. I'm going to put h for hypotenuse. Alright, so I'm going to multiply by h on both sides, and that's going to cancel out. So that's going to give us the velocity of object 1 final on the x-axis. So it's going to be 50 meters per second times cosine of 30. So that's going to go ahead and give us the answer for this velocity on the x-axis, which is really what we care about. So it's going to be the velocity object 1 final on the x-axis. So let's do that in the calculator. Cosine of 30 multiplied times 50 gives us 43.3 meters per second. Alright, so now we have it, 43.3 meters per second. Let's go ahead and once again get the formula for how fast is our archer sliding back. Alright, so our formula, first of all, the initial was 0, so this whole left side was 0. We moved this over and divided by 2, so our velocity for our archer is going to be again m1 v1 final over m2. Alright, but it's going to be the velocity on the x-axis right here. Alright, sweet, so that's the only change it is to the problem now. So let's plug in our numbers. And mass of the arrow, it was an identical arrow, 0.3 kilograms. Velocity was 43.3 meters per second. And now the mass, 59.97 kilograms. Plug that in and we get our answer. So it's going to be 0.3 times 43.3 divided by 59.97. 0.02, I'm going to round it up slightly to 2 meters per second. The previous answer was 0.025, now it's 0.022. It's less speed, and the reason for that is because some of the speed went into the y-axis component because he was holding it at an angle, so therefore some went into the ground. So that didn't do anything to change the velocity in the x-axis. So that's why it's less speed. Alright, if you were to see this on the AP test, this is worth talking about, is likely that's our formula, but we should have substituted the previous formula for the hypotenuse in there. So that formula really should have looked like this. Mass 1 times velocity for object 1 final, which was the height, and so the hypotenuse, so that was velocity final 1, multiplied times cosine of theta over mass square. So that should have been the formula. If they ask you, we don't want you to actually solve for it, just give us the formula. That would be the formula you're looking for, whereas velocity 1 for final for the first object would have been the cosine theta included with it. Alright, that takes care of part B. Let's go ahead and move along now to problem number 9. Would firing a heavier arrow necessarily increase the recoil velocity? And the answer is yes, yes it would. If you fire a heavier arrow, the archer is going to slide down even at a quicker rate. Yeah, if you increase the mass of the arrow right here, m1, and notice it's in the numerator, that will increase the velocity, the recoil velocity. So yes, a heavier arrow would have made the archer go back quicker. Alright, let's go ahead and move along to problem number 10. In this one, it says a 70 kilogram man and a 55 kilogram woman holding a 2.5 kilogram purse on ice skate stands facing each other. If the woman pushes the man backwards so that his final velocity is 1.5, with an average force, with what average force did she push him, assuming they were in contact for 0.5 seconds. Alright, so let's go ahead and work this problem out. We're going to begin by writing down everything we know about this problem. So, the man, mass of the man, I want to go ahead and put M with a M for man, is 70 kilograms, so he's heavier than the woman. It says, and the woman, she weighs 55 kilograms. So mass of the woman, 55 kilograms. And she's holding a purse. So mass of the purse is going to be 2.5 kilograms. A little bit over 5 pounds. This, again, they're standing on ice so that we can ignore friction. That's the reason why they keep saying that. It says if the woman pushes on the man backwards so that the final velocity final, so that his final velocity, so the velocity final of the man is equal to 1.5 meters per second. What is it? What average force did she push him with? All right, so force equals question mark, and they were in contact for 0.5 seconds. By the way, not given here, but assume this initial velocity for both 0.0 meters per second. They're both at rest. She pushes him, and he is sliding. All right, let's do a quick diagram. So here's the man. Here's our woman. She pushes. There's the purse. All right, they are on skates. So he's going towards my right, which is positive. So final velocity for the man, 1.5 is positive. So our answer, I believe in part B they're going to ask us what's the velocity of the woman. That was going to be negative because it's going in the opposite direction. Alright, so let's go ahead and work this out. So we got all this information. I want to know what is the force. Alright, so force times time is equal to change in momentum. We know that formula. Alright, so we're going to go ahead and use that. Alright, so the change in momentum, it's mass as velocity final minus velocity initial. Alright, so that's what we need, the velocity final. Alright, so now that we have that, we're going to go ahead and move the time over to the denominator. And that's going to go ahead and give us the formula for the force. That's part A of this problem. Alright, so this is the force that was applied on the man. So all the information that's going to go in there is information for the man. Alright, so for example, the mass. It's going to be the mass of the man, which is 70 kilograms. Velocity final is 1.5 meters per second. Velocity initial, 0 meters per second. And the time that she made contact was only for 0.5 5 seconds, half a second. Alright, so that's going to go ahead and give us the answer for the force that was applied to the man. So it's going to be 1.5 minus 0 is the same, times 70 divided by 0.5. So it gives us a value of 210 newtons. And that's how much force she put on the man. The force was 210 newtons. Notice how it's positive because she put the force that direction towards the right, which we said that's going to be positive, towards the left is going to be negative. Alright, so that is part A. Let's go to move along to part B. Part B, they ask you, what is a woman's recoil speed? So after she pushes away from him, what will be her speed, assuming it's a closed system? Let's go ahead and figure that out. So now we're looking for her speed. Alright, now what formula should we use? They were together first. So it's going to be mass of 1 plus mass 2, velocity initial. It's equal to, now they're separate, so I'm going to give them 2 mass of, let's put this one as man times velocity of the man final, plus mass of the woman, plus multiply times velocity of the woman final, and that's what we want to solve for. What is her final velocity? So initially, they were started from rest, so that this whole left side is going to be a 0. Alright, so 0 equals mass of the man times velocity of the man final, plus mass of the woman times velocity of the woman final. And so we want to isolate this velocity of the woman final. So I'm going to move this left side over here, and so it ends up being negative. It's equal to mass of the woman and velocity of the woman final, and that's what we're solving for. So now I'm going to go ahead and get rid of the mass of the woman, so I'm going to divide both sides by the mass of the woman. That cancels out, and that's going to go ahead and give us our answer. Mass of the woman. By the way, mass of the woman, at this point in the problem, in part B, she's still holding on to her purse. So it's really, I'm going to add up the 55 plus the 2.5 because she's still holding on to that purse. It's not till part 3 where she throws the purse at our male skater. I don't know what he said, but it wasn't good. Alright, so here's our formula. So it's going to be mass of the man times velocity of the man final divided by the mass of the woman with her purse. Alright, so let's plug in the values. Negative right there, and we expected she's going to recoil to the left, so it was expected that she would have a negative velocity. Mass of the man is 70 kilograms. We're going to go ahead and multiply that times his velocity, which was 1.5 meters per second, divided by the mass of the woman, which is this, plus she's holding a purse. So it's really going to be 57.5 kilograms. So velocity of the woman final is going to be negative. Let's plug it into the calculator. 70 times 1.5 divided by 57.5. She's going to have a velocity of 1.83 if you round it off a little bit. So I'm going to write that over here. Velocity of the woman final, negative 1.83 meters per second. Why is she going faster than the man? Because she's a little bit lighter than the man. So even though the same but opposite forces apply to both of them, she is lighter, so therefore she picks up a little bit more speed. That's why these two do not match. Alright, let's go ahead and move along now to part C of this problem. She throws her 2.5 kilogram purse at him at an angle of 20 degrees above the horizontal and at 4.2 meters per second relative to the ground. What is her speed now? Alright, so she's quite upset. She pushed him away and now she throws a purse. Alright, let's do a diagram for this scenario. So here she goes, sliding backwards in her skates. There's no friction. And she has launched the purse at him. The purse had a mass of 2.5 kilograms. Now, again, initially they were together and then she threw it. Alright, she is heading in the negative direction. The purse now is going in the positive direction. So I want to know still, what is her velocity now? she had an initial velocity before she threw the purse of 1.83 meters per second. What will be her velocity now? All right, so for this problem, let's see, they started together, her and her purse. So it's going to be mass of object 1, which is, I guess, purse plus mass of the woman, and velocity initial, both of them put together. And then she throws it. Now there are two separate objects, mass of the purse plus velocity of the purse final. And that's going to go ahead and be plus mass of the woman multiplied times velocity of the woman final. Again, we're solving for it after she throws the purse. So that's what we're going to go ahead and solve for. All right, in this problem, first of all, velocity of the purse. We need it in the x-axis. Again, because she threw it at an angle at 20 degrees. We don't really care about the velocity on the y-axis because that's just going to be overcome by the normal force. We want to know what is the velocity of the purse on the x-axis because that's going to affect the woman's velocity on the x-axis. So now, again, this one, velocity final, is really this. She threw it at 20 degrees and it was at a velocity of 4.2 meters per second. The angle was 20 degrees. We want to know the velocity of the purse final on the x-axis. That's really what we need. The velocity of the purse final on the x-axis. Alright, and this is the velocity of the purse final after it's been thrown. Alright, so how would you plug this in? It's going to be, notice that the angle is adjacent to this side, and there's the hypotenuse, so it's going to be cosine of 20, because they are adjacent. It's equal to velocity of the purse final on the x-axis over velocity of the purse final. So again, to isolate the velocity on the purse final on the x-axis, we're going to go ahead and multiply by velocity of the purse final on both sides. Alright, so now that we have the formula, let's go ahead and solve for the velocity final for the woman. And we're going to move this whole side over, so it's going to look like this. mp plus mv multiplied times velocity initial is going to be minus mp velocity of the purse final times cosine 20. And that's going to, I should really put a theta right here. Let me do that. It's equal to mass of the woman times velocity of the woman final. And now at this point what we're going to go ahead and do is just divide by the mass of the woman over this whole thing. And there is our formula for the velocity of the woman final. Alright, that is our formula right there. Let me step out of the way so you can see it. From there now it's just plugging in numbers to go ahead and solve for this. Alright, so let's go ahead and do that. Velocity of the woman final is equal to, let's see, mass of the purse, which was 2.5 kilograms, plus the mass of the woman, which is 55 kilograms. Velocity initial of both of them, remember that was, she had already pushed off from the man, so she did have a velocity, minus mass of the purse. So this is going to go ahead and be 2.5 multiplied times cosine of 20. Sorry, 2.5 multiplied times velocity of the purse, which was 4.2 times cosine of 20. There we go. And this whole thing's going to be divided by the mass of the woman, which was 55 kilograms. Alright, so there we have it. From here, just plug it into the calculator. I might do it in multiple steps. Mass of the woman final. So let's see, we got 55 plus 2.5 times 1.8. It's going to go ahead and give us negative 105.23 minus, it's going to be 2.5 multiplied times 4.2 times cosine of 20. That gives us the following, 9.87 divided by 55 kilograms. So put both of those together. divided by 55, and it gives us her velocity, which is negative 2.1. I'm going to round that off to that, 2.1 meters per second. And yeah, she increased her speed from 1.8 to 2.1 because after she throws it in the opposite direction, she's going to recoil back. All right, that takes care of problem C. Up next, let's go ahead and work on problem number 11. In this problem, we're asked the following. It says, a dart of mass md is launched straight upwards towards a block of mass mb that hangs at rest from a string. And this is going to be a figure for it in the next slide. It says, immediately before the dart collides with the block, the dart has a speed of VO. The dart then collides with and sticks to the block, and the dart block system travels upwards to a height of h before the system comes to rest, as you see in the figure. So there's the beginning, there's the end. So it travels a total of h of height. Alright, so they ask you as the following, what is the change in momentum of the dart block system immediately before the collision to the instant where the system comes to rest? Alright, so we're looking for the change in momentum. Alright, change in momentum, delta P, it's equal to momentum final minus momentum initial. Alright, so to solve for this problem, first of all, picture these guys. What is the velocity at the end of the collision? Alright, the answer is the velocity is 0. It's got no momentum. Alright, so it's just really, all you need is the momentum initial to go ahead and solve for this problem. And momentum, it is mass times velocity, and there you have it. So that's really what you're looking for. So here we go, mass times velocity. The answer for the problem is letter B. Alright, let's go ahead and move forward now. It says, in problem number 12, it says, two identical spaceships are traveling in deep space, far from any planet or stars. The ships travel in the same direction, with the slower one directly behind the faster one. The ships are connected by a cable attached to a spool, so that the part of the cable outside the ships can be made longer or shorter as needed. The cable is used to bring the ships to the same speed for a transfer of cargo. The graph above shows the speed of the two ships during a 10-second interval. Thus, at least one of the ships have its engine turned on during the time interval as shown, and what evidence indicates so. Alright, so check out the graph. We have velocity as a function of time, and the velocity of the first ship is 80-10, the second ship is 79-90. Alright, so if I were to ask you, what is the average velocity? Well, you would say, well, between both of these, it would be 8,000 meters per second. Alright, that's the average velocity when they first begin their transfer. But if you look at the graph for the slower ship, it goes a little quicker. The faster ship begins to slow down a little bit. But here, what's their average speed? It is 8,005 meters per second. So initially their velocity was 8,000 meters per second, but 10 seconds later their velocity, the average velocity is 8,005 meters per second. So there was an increase in velocity. So the answer would be yes, and it's actually letter B, yes, because one of the ships did have the engines on, and the reason for that is because the momentum of the two ships increased. So if it has more velocity, it has more momentum. Alright, so that's the answer for this problem, letter B. In problem 13, it says a force probe is used to push a box across a smooth surface, as shown in the figure, which is in the next slide. Now, the frictional forces are considered to be negligible, so we're going to go ahead and ignore it. The force probe collects data about the force exerted on the box as a function of time. The data are used to create a graph as shown. During which time interval does the box experience the greatest change in momentum? Alright, so here's our graph, and you see that, and that. So I want to know during what time interval is it between 0 and 2, 2 and 4, 4 and 6, or the change in momentum is the same on all these time intervals. Alright, so they want to know again the change in momentum. So we have force here as a function of time, so force times time is equal to our change in momentum. So again, we have to multiply them together. So are we looking for the slope of the line, or are we looking for the area under the line? If you're multiplying them, then you're looking for the area under the line. If it were force over time, then you'd be looking for the slope, but that's not what they want here. They want to know the change of momentum, which is force times. So we're looking for which one of these sections has the greatest area under the line. So that will be between 4 and 6. That'll be the greatest area under the line. So that'll be the answer for this problem is letter C. Alright, finally let's go ahead and move along to problem 14. In this one they ask you, how does an air mattress protect a stunt person landing on the ground after a stunt? So here we have our stunt person jumping from a helicopter to an air mattress there. Alright, so how does that work? The answer is this. If we increase the amount of time, so I'm going to isolate the force. If we increase the amount of time, the force will decrease because they're inversely proportional as this formula is set up. So as the collision takes longer, therefore there will be less force exerted on the stunt person. Alright, so that's part one. If we increase the amount of time for the collision, therefore the force will decrease. On top of that, to decrease the force further, they're going to go ahead and spread the force over a larger area. So when he collides, now it's no longer just this one small mattress. Notice how they make it very big, so he has a larger area. So if you increase the area, you can dissipate more force. So for this one, the answer for this one, it's letter E. It lengthens the stopping time, so it takes more time, lengthens it, the stopping time of the stunt person, and reduces the force applied during the landing. So more time equals less force. So therefore, there is less harm to the stunt person. Alright, that takes care of this question, and this also brings us to the end of our lesson. Thank you so much for watching.